Welcome to Lecture 4 of our Week 4 on sequences. This lecture will focus on some properties of how limits behave. I will not be exhaustive in proving every single fact about limits. After all, that is not the purpose of this course. Many of these limit properties you have already encountered in Calculus 2. What we will be concentrating on is how we can demonstrate that these properties hold using the rigorous notion of convergence and limit that we described earlier this week. Due to time constraints, not all of the possible combinations of statements will be given. I encourage you to take a look at your textbook, pages 42 to 50, to check out some of the other statements and proofs. When working on the exercises and problem set for this week, you certainly should consult the textbook for ideas on how to approach the problems. Treat this lecture as a sampler of some of the things that we can do. The first one of this lecture is the famous squeeze theorem. Suppose we have three sequences xn, yn, and zn. They are arranged so that term by term, xn is less than or equal to yn, which is less than or equal to zn. If we know that xn and yn, the smallest and the largest of the three, both converge to the same limit, then we can conclude that yn should converge and share the limit. For convenience in notation, when giving the proof in the next slide, we will use capital L to denote the known limit of xn and yn zn, and also the putative limit of yn. Before showing you the proof, it may be worth taking a pause and thinking about how we should approach proving this theorem. What do we know? We know that two sequences converge to the same point. This means that if we specify a tolerance epsilon, separately, x and z would eventually both end up within distance epsilon of the limit L. But if y is between x and z are both in the same interval, then y should also be in the same interval. Let's try to now make this argument precise. Start from epsilon positive. Our goal is to find an index such that beyond that index, we have the terms of y are within distance epsilon of the limit L. Since we know that x and z are converging, we can apply the definition to find n sub x and n sub z. They are chosen so that for indices larger than n sub x, the terms of x are within distance epsilon of L. And for indices larger than n sub z, the terms of z are within distance epsilon of L. So if we set n sub y to be the larger of n sub x and n sub z, if an index p is greater than n sub y, it has to be larger than both n sub x and n sub z. So by the previous step, we know that for the index p, the term x sub p and z sub p are both within distance epsilon of L. The condition of within distance epsilon of L can be rewritten as both x sub p and z sub p being bigger than L minus epsilon and less than L plus epsilon. On the other hand, since z sub p is no less than x sub p and y sub p is sandwiched between them, we must then have that y sub p is between L minus epsilon and L plus epsilon for p bigger than n sub y. Rearranging the inequality, we see that it is exactly saying that the distance between y sub p and L is less than epsilon, and this shows that y sub p converges to L since epsilon is arbitrary, and this proof gave a procedure of how to pick n sub y to make the condition hold. The key idea that shows up in this proof is the use of the maximum in step 2. When you try to prove a statement that has as hypothesis that multiple sequences are convergent, one problem is that for a fixed epsilon, the n that shows up in the definition of convergence for the different sequences may be different. one sequence may take only 10 terms before it gets to within 1/1000th of the limit. The other sequence may take 30 million terms before that happens. The nice thing when dealing with convergent sequences is that we're dealing with eventual behavior. For a finite list of converging sequences, no matter how poorly individual sequences can behave, by taking the maximum of the n that they each generate, we can always find an n large enough that all of the sequences in the list simultaneously satisfy the closeness condition to the limit for the same epsilon for any index bigger than the n we found. This idea will come up a few more times this lecture. The next theorem concerns the arithmetic operation of taking square roots. Suppose that x sub n is a sequence all of whose terms are non-negative. That y sub n be the sequence whose terms are the square root of the corresponding terms of x sub n. This is why we assume that x sub n has non-negative terms. This allows us to take square roots without worries. Then, if x sub n converges, y sub n converges to the square root of the limit of x. Most arithmetic operations respect taking limits. This theorem is the first of two we will prove in this lecture concerning arithmetic. The general rule of thumb is that for the usual arithmetic operations, provided that we're dealing with convergent sequences, taking the limit first and then evaluating the arithmetic versus doing the arithmetic term by term first and then taking the limit will give you the same result. In this theorem, we claim that this is true for the square root operation. Prior to the proof, we need to perform some preliminary computations in preparation. We will write using capital L for the limit of the sequence x sub n. Our goal then is to prove that the limit of the sequence y sub n is the square root of L. So it is instructive to try to compute the difference between y sub n and the square root of L, since this will show up as the condition we need to check. Using that y sub n is the square root of x sub n, we find ourselves with a difference of two square roots. To handle this, we will use a trick known as the rationalization of the numerator. This is the opposite of the rationalization of the denominator trick that you have frequently used in college algebra. I will talk about why this is useful in a bit. To implement the rationalization process, what we do is notice that the difference of two square roots can be simplified using the formula a squared minus b squared is equal to a plus b times a minus b. So we multiply our difference in square roots by the conjugate. That is, we multiply and divide by square root of x sub n plus square root of L. Expanding and simplifying, we come to the conclusion that the quantity y sub n minus square root of L can be rewritten as the quantity x sub n minus L divided by the quantity square root of x sub n plus square root of L. The benefit to this form is that since we know that x sub n converges to L, we can use the definition of convergence to replace the numerator by an epsilon. The denominator is good because it is the sum of two positive quantities, so it can never be worse than either of the individual terms. So to prove that the distance from y sub n to square root of L is less than epsilon is the same as proving that this fraction in absolute values is less than epsilon. Keep this fraction in mind. Now, let us start the proof. Given the epsilon that we need to treat, first we define a delta by setting it to square root of L times epsilon. Then, by the convergence of x sub n, we can find a capital N such that for later indices, the distance between x sub n and L is less than delta. We can now substitute back delta equals epsilon times square root of L, and we further can make the larger side even larger and not falsify the inequality. So instead of square root of L times epsilon, we can enlarge it and say that the distance between x sub n and L is less than epsilon times the quantity square root of x sub n plus square root of L. But if we rearrange using the computation on the previous slide, we see that this is precisely saying that the distance from y sub n to square root of L is less than epsilon. And this shows that the sequence y sub n, whose terms are the square root of the terms of x sub n, must converge to the square root of the limit of x sub n. Some of you may have noticed this already. There is one thing about this proof that isn't quite right. I've left a question about this on the exercise sheet for this week. Go take a look at it and see if you can figure out what the problem is and how to fix it. This is our second arithmetic theorem. In this theorem, we show that if we add two converging sequences term by term, the resulting sequence is still converging and converges to the sum of the limits of the original sequences. For convenience, we will use capital X to denote the limit of x sub n and capital Y to denote the limit of y sub n in this proof. Before we read through the proof, notice that this theorem again features two initial sequences and are assumed to converge. As we mentioned a few minutes ago, in situations like this, we will need to combine their indices using the max function to find an index such that both sequences are close to their limits. Let's pay attention and see if we can notice where this is used. First, we start with epsilon. This is the epsilon that we want in the end. I will start by defining delta to be epsilon divided by 2. Using this delta as the input to the sequence, to the convergence of the sequences x and y, we can find n sub x and n sub y such that when evaluated at an index later than n sub x, the term of the sequence x is no more than delta away from the limit capital X. And when evaluated at an index later than n sub y, the terms of the sequence y is no more than delta away from the limit capital Y. To prove that the sequence z sub n, which I remind you is this one formed by the term-by-term sum of x sub n and y sub n, converges to capital X plus capital Y, we need to evaluate the difference z sub n against the putative limit. When doing so, we first replace z sub n by its constituent x sub n and y sub n. Then we can apply the triangle inequality. For those of you who don't remember, this is listed as proposition 8 on the usable formula sheet. Grouping x sub n together with capital X and y sub n together with capital Y, we arrive at the upper bound that the distance from z sub n to capital X plus capital Y is less than the sum of the distances from x sub n to X and y sub n to Y. Now, if we evaluate this inequality at an index p that is larger than the bigger of n sub x and n sub y, the inequalities shown in step 1 need to hold since p is large enough. So, the inequality in step 2 leads us to the statement that the distance from z sub n to the sum of capital X and capital Y is less than twice delta. One delta coming from each of x and y. Since 2 delta is equal to epsilon, we have demonstrated that for any epsilon, we can find an index such that beyond that index, the sequence z sub n is closer than epsilon to the putative limit, and hence convergence is proven. Before moving on, I want to point out a few things. Students reading this proof often wonder how I come up with the substitution delta equals epsilon over 2. Or in other words, how did I figure out these intermediate replacements of epsilon so that in the end everything adds up to epsilon again? This is about 1 part experience and 2 parts trial and error. For example, if you just start with using epsilons for the convergence statements for x sub n and y sub n instead of using delta, you can complete your proof, and at the very last step, you realize that now instead of epsilon distance, you have 2 epsilon distance. Since you find yourself to be off by a factor of 2, it would seem reasonable to go back to the construction and make sure that when you use the convergence of the known to converged sequences, you be a bit more stingy and give each of the sequence half of the tolerance you did before. Sometimes it may be the case that you have to adjust several times, accounting for the ways different formulae interact before finding the right distribution of tolerance among the constituent parts. Another point I want to make is that in step 2, you just saw a use of the triangle inequality. This inequality will come up over and over again in this course and is one of the most used tools in analysis. Make sure you are confident with manipulations of inequalities using the triangle inequality as a tool. The final 2 theorems we will discuss this week have to do with multiplying sequences. But this time, we will perform multiplications with one of the factors being a divergent sequence. The first theorem multiplies together, term by term, the 2 sequences x and y, with x sub n converging to 0 and y sub n possibly divergent, but bounded. An important remark. Earlier, we demonstrated that convergent sequences must be bounded. The converse is not true. Bounded sequences may be divergent or may be convergent. It depends on the precise sequence. We claim that the product sequence will still converge to 0. The basic idea behind this theorem is that 0 times anything finite is equal to 0. The proof is quite short. In step 1, we state the condition for the y sub n sequence to be bounded. We use the letter m to denote the number that is bigger than the absolute values of all the terms of y sub n. Now, we let epsilon be an arbitrary positive number. Our goal is to show that the product x sub n times y sub n is no more than distant epsilon away from the claimed limit, which is 0. What we will do is make use of the convergence of x sub n. First, we set delta to equal epsilon divided by m. Then, applying the convergence property, we can find an index n such that for all later indices, the absolute value of x sub n is no more than delta. That we get a control on the absolute value is because the limit is 0 by hypothesis, so x sub n minus 0 is equal to x sub n. Now I claim that with the same capital N for all later indices, the absolute value of z sub n is less than epsilon. This is because z sub n is the product of x sub n, which is less than delta, against y sub n, which is less than m. So the product is less than delta times m, which is epsilon. This is precisely what we need to prove to conclude that z sub n converges to 0. Our final theorem again multiplies a convergent x sub n with a divergent y sub n. This time, x sub n converges to a non-zero number, and y sub n not only diverges but is unbounded. Recall that every unbounded sequence diverges, but not every divergent sequence is unbounded. The theorem concludes that the product sequence must also be unbounded, and hence divergent. Roughly speaking, this theorem is the sequence analog of the expectation that if we multiply infinite against anything non-zero, we get something that is infinite again. The proof of this theorem is a bit more complicated. It turns out that the definition of being unbounded is a bit harder to manipulate. Thankfully, its negation that a sequence is bounded is easy to manipulate. And so we are led to using a proof by contradiction to take advantage of this. First, we do some prep work. The idea behind the first two steps is that if the sequence x sub n converges to a capital X, which is non-zero, then eventually all the terms x sub n becomes close to capital X. And in particular, they must all stay away from zero, since the sequence can only have one limit. To capture this idea, we first set epsilon to be equal to 1/3 the absolute value of capital X. Then we can find some index n such that for all later indices, the distance from x sub n to x is no more than epsilon. Doing a little bit of gymnastics with the inequality, we see that since we can write capital X as the sum of x sub n with the difference between capital X and x sub n, using the triangle inequality, we can see that the absolute value of capital X is less than the absolute value of x sub n plus epsilon. Plugging back in our choice of epsilon, being 1/3 of absolute value of x, and rearranging, this shows that absolute value of x sub n is at least 2/3 the absolute value of capital X. In particular, x sub n cannot be too close to 0. Why is this important? Because if x sub n is not too close to 0, and it multiplies something that may go toward infinity, the resulting thing will still be unbounded. Let's prove that this is true, that the product sequence is an unbounded sequence. We proceed by contradiction. Suppose, for contradiction, that the product is bounded. So there is some capital M that is larger than the absolute value of z sub n for all natural numbers n. Using the definition of z sub n as a product, this means that the product of the absolute values of x sub n and y sub n together is less than m. When the index is bigger than capital N, which we found in step 1, we can use the conclusion of step 2. This means that 2/3 absolute value of capital X times the absolute value of y sub n is less than m. Since capital X is not 0, we can divide by it. And this shows that when the index is past capital N, the absolute value of y sub n must be bounded by 3m divided by 2 capital X. We are not quite done, but we ran out of space, so let's compress things a bit by removing the justification for the steps we finished already and hide some statements that we no longer need. By step 6, we have shown that all indices past the capital N that we found in step 1, the absolute value of y sub n is bounded. To conclude the proof, we need to show that there is a bound for the remaining terms of y sub n. But there are only finitely many terms that were not accounted for. Having accounted for all indices that are greater than capital N, there are only n terms left. And as we know, any finite set of real numbers contain a maximum. So in particular, these numbers are bounded above by some number p. So combining the results from steps 6 and 7, this would imply, where the contradictory supposition is true, that z sub n is bounded, that the sequence y sub n is also a bounded sequence. But since we assume that y sub n is unbounded, this means that the supposition is wrong, and z sub n must be unbounded after all. Okay, that's it for this lecture. Thank you for your attention listening to this longer than usual lecture. That's the end of this week's videos. I will see you next week.